Okay, so balancing reactions and knowing the types of reactions that they are is all very, very helpful. And when we get to predicting products, which is what we're starting now, those skills are basically essential because we're going to be given very limited amount of information. And from that limited information, we're going to have to complete the entire reaction, make sure that the formulas for the products are written correctly, and finally, be able to balance it. So that's a lot of different things that hinge on our ability to um, identify the type of reaction and to write correct formulas and, of course, to balance them. So to start off, what it says right here, very important, do not forget that there are seven, oops, always a great way to start out a video. There are seven elements that exist in the diatomic form that when they are not in a compound. Now remember, these seven, when they're in a compound, their numbers on the bottom could be anything. But if they're by themselves, not in a compound, they always are diatomic, right? So again, you all know that the silly word is Brinkelhoff. We have bromine, we have iodine, we have nitrogen, we have chlorine, hydrogen, oxygen, and fluorine. So there's the Brinkelhoff. Those seven, again, when they're by themselves, always are going to have a little two by themselves. But just to repeat, just because it's like this doesn't mean when it's in a compound bound with another element, another atom, it's going to necessarily get a two. It doesn't, okay? Not necessarily. Also, be sure to write the correct formula for each product. I cannot stress how important this is. If we know what the product should be, we have got to be able to get it to be written correctly because that will really, really hinder our ability to balance the reaction. And besides, it would just be wrong anyways, right? If you don't have the right products, well, you don't have the right reaction. You won't have the right balancing. And it just, again, just kind of compounds upon itself. So let's start with the easiest reaction in order to predict the products because all the products are always the same. And so, like I said, these are really the easiest. And those are combustion reactions. Just as a reminder, a combustion involves some sort of hydrocarbon. Again, I put little X's there because it could be any number of carbons and any number of H's. It's just going to be a hydrocarbon. That's what we call it. It's going to react with oxygen. Again, you have to have oxygen in order to have combustion. And it's going to make the same two products every single time, which are water and carbon dioxide in either order. So like it says here, combustion reactions always need oxygen in the reactants. Again, in the absence of oxygen, you have no fire. And water and carbon dioxide are always products in a carbon combustion reaction, always, every single time. So let's go ahead and try to complete and balance the combustion reactions of some of these, okay? I'll do some, I'll let you guys do the other ones. So to start off with the easiest one, we have methane. Methane, it tells us, is going to be CH4. Okay, then I know if it's going to be a combustion reaction, I must have oxygen in order to burn. Then I'm going to have two products, CO2 and water. Again, it does not matter what order I put the products, carbon dioxide, water, or water and carbon dioxide. It's the same exact thing, right? Now to balance this, again, I'm going to go ahead and do my carbons first. So I have one on each side. That looks good. My H's next. I have four H's on the left, so I need four H's on my right because 2 times 2 gives me 4. What that does is now I have my oxygens. Here I have 2 oxygens. There I have 2 oxygens. That makes 4. So I need a 2 there to give me 4. So that is a proper balanced chemical reaction or chemical combustion of methane. So let's try another one. So here we're going to have propane, C3H8. If it's combustion, I'm going to have to react it with oxygen. Then it's going to burn to give me carbon dioxide and water, or of course, water and carbon dioxide. All right, to balance this thing, I'm going to do my carbons first. So here I have 3 carbons. I'm going to need 3 carbons to balance. My H's next. I have 8 H's on the left, so I need 8 H's on the right because 4 times 2 gives me 8. The last thing I'm going to do is my oxygens. Here I have 4 oxygens. Here I have 6 oxygens because 3 times 2 gives me 6. So 6 plus 4 gives me 10. So I would need 10 there because 5 times 2 is 10. There again is a balanced chemical combustion of propane. So you get the idea. Again, these are not difficult at all in order to predict. If you know it's a hydrocarbon, then again, this part is going to be identical on every single one, including number 3 and number 4. Guess what? It's either ethyl alcohol or octane plus O2 yields water and carbon dioxide. Okay? Again, those are pretty easy. I like those because, again, it doesn't take a whole lot of thought. All right, the next type we're going to go over, excuse me, is called a synthesis reaction. We need to predict what this is going to be. Now, if you remember what a synthesis reaction is, it is basically we are going to be reacting and chemically combining two smaller components, whether it's two individual elements or two small compounds into a larger compound. We're going to synthesize them into something bigger. So for number 1, we have our first example is Mg plus O2, magnesium plus oxygen. So the only thing we could really do is put them together, right? So magnesium and oxygen. What I would need to do now, of course, is start with the periodic table. Magnesium is a +2, group 2 alkaline earth metal. Oxygen is a -2. So if I cross that, what I get, of course, is just MgO. They cancel out, not Mg2O2, but just MgO, because again, I don't need 2 of each. I need 1 of each because again, it's just a ratio, right? Just for every 1 magnesium, I need 1 oxygen. It's a 1-to-1 ratio, so we reduce it down. So that is just, of course, MgO. Now to balance it, of course, I have 2 oxygens there, so I'm going to need a 2 there. It gives me 2 oxygens on both sides, and now I have 2 magnesiums. That is a balanced chemical synthesis of magnesium and oxygen to make magnesium oxide. The next one we're going to do is we have lithium plus oxygen. So of course, that's going to be lithium and oxygen. Let's go ahead and double check our charges. Lithium is a group 1, oxygen's a -2. So I'm going to cross that down there, cross that down there. So what I really get is going to be Li2O. That's what it really is going to be, Li2O, because the 2 of the charge of the oxygen. So now that I know that, I'm going to go ahead and go back and balance. I have 2 lithiums, so I need 2 lithiums. I have 2 oxygens. Uh-oh, dang it. So that's not going to work, right? Because if I put a 2 there, now I just unbalance my lithiums. So what I need to do is not start with my lithiums. That did not help. I'm going to go ahead and start with my oxygens. So I have 2 there, so I need 2 here. I'm going to put a 2 there. But what I did now is I doubled my lithiums. 2 times 2 gives me 4, so I need 4 lithiums. That's the balanced synthesis reaction of lithium and oxygen to produce lithium oxide. A 4-to-1-to-2 ratio. Again, that's the only way it's going to balance. Let's go ahead and do one more. Iron plus chlorine. Iron plus chlorine is going to give me iron and chlorine. They're not giving me the charge of the iron. So I'm going to guess it's a +2. I'm going to make an educated guess that this is a +2, and that's a -1. So that's going to go down there. That's going to go down there. So the final compound for this, if iron is in fact a +2, would be FeCl2. Okay, because again, the charge of the 2 of the iron. Again, operating the assumption that iron has a +2 charge. They would kind of need to tell us that, wouldn't they? All right, so let's go ahead and balance that. Again, operating the assumption that my iron is a +2. Let's go ahead and keep going forward. So here, my chlorine has 2, my chlorine has 2, my iron has 1, my iron has 1. Hey, look at that. It's already balanced. That's nice. So iron plus chlorine gives me FeCl2, or iron 2 chloride. So that's how you balance and predict the products of synthesis reactions. Now, the way I would know that this is a synthesis reaction is because we have 2 individual elements. What else can you do, right? There's nothing else you can do with 2 individual things other than put them together. So that's a synthesis reaction, right? That makes sense. Okay, the other, on the opposite, we have the decomposition reactions. Again, using the same logic, if I have a compound, what's the only thing I could do? If I have a single compound, I can't rearrange that compound because it's really only one way it could go together. So clearly the only thing I could do is break it apart. So we're going to go ahead and break apart these compounds to make a decomposition reaction. So for the first one, we have MgO. This sounds kind of familiar, doesn't it? MgO, I'm going to be left with Mg and O. Okay, that's pretty easy. I decomposed magnesium oxide into magnesium and O. Now, hopefully some of you will recognize that O is part of Brinkelhoff, and I need a 2. That's oxygen. So magnesium plus oxygen is decomposed from magnesium oxide. So let's go ahead and try to balance this thing. So I notice I have a 2 here, so I'm going to need a 2 there. That balances my oxygens, and now I've balanced my magnesiums. So a 2 to a 2 to 1, that's the decomposition reaction of magnesium oxide to magnesium and oxygen. All right, let's try number 2, or the second one, HCl. So HCl, again, is a compound, and it's only one compound. So again, we have to just break it apart. There is no other option for us to do. We have H plus Cl. Again, think of the 7 diatomic or diatomic elements. Is H part of Brinkelhoff? Yes. Is chlorine part of Brinkelhoff? Yes. So there it goes. There is the correct reaction. Now to balance it, all I need to do is put a 2 there and it's balanced. That's pretty obvious. Now I have 2 H's, 2 Cl's. That's a balanced chemical decomposition of hydrochloric acid into hydrogen and chlorine gases. The third one, we have water. Water would decompose into its individual elements of H plus O. Again, just like before, H is a diatomic, O is a diatomic, Mg, remember, is not. That's why it doesn't get a 2 there. So to balance this thing, I would need to balance my O's. There we go. There we go. That is a balanced decomposition of water to hydrogen and oxygen. I do want to go over the next one because I just want to remind you guys, do not always put a 2 after these. There are only 7 elements that get it, not the rest of them, okay? So aluminum chloride would decompose into be aluminum and chlorine. Chlorine is one of the Brinkelhoff, so it gets a 2, not a 3. That 3, remember, comes from the charge of aluminum. The aluminum does not get a 2 because it's not one of the 7 diatomic elements. So AlCl3 would decompose to Al plus Cl2. Looks kind of weird, I know, but that has to be the way it goes. The only thing we could do now to balance our chlorines is if I have 3, is I need to get that to be an even number of 6. If I need to get this to be a 6, I do that. So 2 times 3 gives me 6 chlorines. 3 times 2 also gives me 6 chlorines. So the chlorines are now balanced. All I need to do is balance my aluminums, and there we go. That is the correct decomposition of aluminum chloride to aluminum and chlorine. All right, so that's a decomposition reaction. Remember, it's very easy to spot because basically, again, you have an individual compound. What else can you do with it other than break it apart? Similar to synthesis reactions where you have an individual elements, what can you do? You can't really switch them. If you have Mg plus O, there's no point in putting O plus Mg. It's the same thing. So all you can do is go ahead and put them just together to be MgO. All right, that takes us to single replacement reactions. Now, these do deserve a little bit more attention. The reason why is not all single replacement reactions are going to occur. Occasionally, we're going to have to write no reaction. What no reaction means is that if I put this element with this compound, nothing is going to happen. This element, this metal, is more active than this one, so it's not going to get rid of or release the nonmetals. And so literally you could just put them together, watch them for any number of minutes or hours or weeks or months, but nothing's going to happen. They are not going to react. And the way we know that is by looking at what we call the activity series. This right here. This is in your formula chart. It is on the same sheet as your polyatomics, which are on the left. On the right side is your activity series. So you'll need to look at this, and we only use this only for single replacements. Notice I have not brought it up for combustions. I did not mention it for synthesis or decomposition, and I'm also not going to mention it for the double replacements, only the single replacements. These are the ones you have to wonder, is this reaction going to occur at all? Okay, so let's go ahead and do some examples, and I'll show you what I'm talking about. So this very first one, we have magnesium plus iron 3 nitrate, iron 3 nitrate. Now, again, you guys know from a single replacement, what may happen is this nitrate here may move over to the magnesium, okay? If it does, it would give us MgNO3 2 plus Fe. If it does move, why is there a 2 right there? Because the charge of magnesium is a plus 2. That 3 tells me that it's an iron 3 oxide or nitrate. So just in case you're curious, it's in MgNO3 parentheses 2. But is that even gonna happen? So what we're gonna do is we're gonna come over to this activity series. We're gonna look at the two metals. We have magnesium and we have iron. Magnesium is located right here. Iron is located down here. So because it's going in upward direction, magnesium is more active than iron. Magnesium is higher than iron, meaning magnesium wants to take that nitrate. It is going to steal it from the iron, and the iron is not going to be able to stop it. Therefore, this is the final product. MgNO3 parentheses 2 plus iron. Okay, that is the correct formula for the product of magnesium plus iron 3 nitrate reacted together in a single replacement reaction. All we need to do now, of course, is balance this thing. So we have the biggest compound would probably be this one, FeNO3 parentheses 3. Notice I have a 3 there and I have a 2 there. So to balance that, just like I did in the previous example, I want to get them both up to 6. If I have 3, that's an odd. Double it, then I get 6. That's an even. If I have 2, multiply it by 3, I still get an even, right? So I'm going to go ahead and put a 2 here and a 3 there. 2 times 3 gives me 6 nitrates. 3 times 2 gives me 6 nitrates. So my nitrates are now balanced. But, of course, what I did to my iron and what I did to my magnesium need to be corrected. So there is the correct single replacement reaction that would occur from magnesium reacting with iron 3 nitrate. Okay, let's look at the next one. The next example we have is copper plus zinc 2 chloride. Copper plus zinc 2 chloride, okay? So if it's going to react, the chlorine would move over to the copper and we would get Cu, Cl, I'm assuming the copper is going to be 2, I'm not really sure, plus zinc, okay? But let's double check ourselves. Copper's way down there and zinc is right here. So zinc is higher. Notice zinc already has the chlorine. So in this case, this reaction actually wouldn't occur at all. This would be what we would say is literally no reaction. If I put copper with zinc 2 chloride, nothing's going to happen. There won't be any sort of reaction whatsoever. They'll just sit there and stare at each other and be like, hey, what's up? But they're not going to do anything. There's going to be no reaction whatsoever. So we literally just write no reaction. That's it. Literally, that's it. That's the end. Moving on. The next one, we have Mg and H. Now, I know H isn't a metal, and the activity series looks like most metals, but believe it or not, there's the H. It's the only non-metal on here. And my other one is magnesium. So magnesium is a whole lot more active. So definitely it's going to steal that chlorine and take it. Again, the H is going to have no ability to stop it. So we're going to be left with MgCl plus H. H is one of the Brinkelhoff 7 diatomic elements. Our magnesium, of course, is a +2 because it's a column 2. Chlorine is a -1. So when I cross those down, it's going to be MgCl2. MgCl2 is the correct formula for magnesium chloride. So MgCl2 plus H2. Now remember, this 2 did not come from the diatomic Brinkelhoff 7 elements. It came from the charge of the magnesium because it's in a compound now. The magnesium has an influence over the chlorine. Remember, chlorine can take 1. Magnesium has 2 valence electrons, so you need 2 chlorines for every 1 magnesium, right? So to balance this chemical reaction, what we would need, this is the biggest compound, so I'm going to balance everything to that, is I'm going to need 2 chlorines, so 2 chlorines. That gives me 2 H's. Oh, look at that, I already have 2 H's. That tells me the reaction is balanced. That was easy. All right, the next one we have is copper plus hydrogen fluoride, or hydrofluoric acid is the proper name of that. So I'm going to look at copper and hydrogen. There's hydrogen. Oh, and look, there's copper. Copper is right below it. So hydrogen is more active. Hydrogen already has the fluorine, so this reaction would not occur. Absolutely nothing would happen. You could put hydrofluoric acid on copper, and it will not corrode it. That's good to know. So hydrofluoric acid, which is a very, very strong acid, would not corrode and destroy copper. Okay. The next one we have is aluminum and nitric acid. HNO3 is nitric acid. So again, our two things we're going to look at is aluminum. Aluminum is right here. Hydrogen is right down there. So again, aluminum is more active. So aluminum is going to want to steal the nitrate. So that's going to give us AlNO3. The charge of aluminum is 3, so the 3 will move down here. The nitrate is a 1, so it's going to move right there. I don't need to write the 1, so it's just AlNO3 parentheses 3. Then the H is going to be left by itself. Remember, it is a 7 of the 7 diatomic elements, so it's H2. So that is aluminum nitrate plus hydrogen. That is the correct reaction. We just need to make sure it is correctly balanced. So I'm going to balance everything probably to the AlNO3 parentheses 3. So because I have a 3 there, I know I'm going to need a 3 there to balance my nitrates. What I did is I gave myself 3 hydrogens. 3 hydrogens, and over here I have 2. 3 hydrogens and 2 hydrogens cannot balance. The only way to get that around that is to double both of them. So what I'm going to do is I'm going to go back and I'm going to double this. Okay. So let's see what that does. Now, nitrates. I don't have 3 nitrates. I have 2 times 3. That gives me 6. So I'm going to need a 6 there to give me 6 nitrates on both sides of the reaction. What I did, of course, is I gave myself 6 H's right here. Well, guess what? I could easily fix that with a 3 because 3 times 2 gives me 6 H's. And then my aluminum, I have 2, so I need a 2 there. So that would work. Notice I cannot reduce it. 2, 6, and 2 are all evens. You think, okay, might be thinking, oh, could that not be reduced to a 1, 3, 1? No, it cannot, because the 3 on the H2 is not divisible by 2. So 2, 6, 2, 3 is the lowest ratio. And the only way we could write the properly balanced and properly written single replacement reaction of aluminum and nitric acid, making aluminum, nitrate, and hydrogen. Okay? So one last one again, I want to go through this one last example. We have silver, we have hydrogen. Again, if we look at the activity series and we try to figure out which one is more active, the one that is more active will take or keep the non-metals. So my silver is way the heck down here, not a very active metal, obviously. Notice gold is the least, which is why gold does not rust or tarnish. Neither does silver, right? So that's why your jewelry looks really nice. You don't have to keep cleaning it because it doesn't corrode over time with reactions to your skin, your sweat, or the atmosphere. So anyway, here we have H. So H is more active than silver. So H is going to want to take or keep. Notice H already has the sulfate. Therefore, what we would have to say for this one is just simply no reaction. This would not do anything. Sulfuric acid and silver, again, would have no effect. The sulfuric acid would have no effect on the silver. Again, this is very good if you do a lot of work with acids. Knowing exactly what acids will and will not corrode is a very, very useful thing to know. All right, there is one thing I want to point out before we move on. The halogens may replace halogens, okay? Halogens may replace halogens. So in this particular case, what we have is fluorine gas plus sodium chloride. What we're going to get, again, if we look on here, we're not going to find fluorine on our activity series. We're not going to find it, but we will find sodium. But what good is that? Because sodium's right there, but there is no other thing on here. There's no chlorine. There is no F. So what do? We're going to move the chlorine, or sorry, not the chlorine. The sodium is going to move here. So what we're going to be left with is NaF plus Cl2. Cl2, you're saying, well, because again, it's one of the 7 diatomic, just like F2 is, which is why we have a 2 there, right? Because again, it's the diatomic elements. It does not get it there because again, it's bound with sodium. Remember, just as a review, sodium, of course, is a +1 Fluorine is a -1, therefore they cancel out. So it is just NaF yields, or excuse me, plus Cl2. Another example, K2 plus Kf. Let me go ahead and clear all this. Br2 plus Kf, Br2 of course, because again, it is a diatomic element. We're gonna move the potassium over there. So what we get is a potassium bromide plus fluorine. Fluorine is one of the diatomics. Sorry, that my F looks pretty ugly. There we are, that's a 2. Screen messes up down here. K, let's just double check that. K is a +1, bromine is a -1. They do cancel out. So that is the correct way to write the single replacement of bromine plus potassium fluoride yields potassium bromide plus fluorine. To balance this, there we go, and there we go, balanced. Okay, so those are the single replacements. Again, you have to look at the activity series to see would the reaction even occur in the first place. If the more active element, just review, if the more active element already has the non-metal, in this case the fluorine, the chlorine, the fluorine, or whatever, then the reaction would not progress. If the metal that is more active does not already contain it, then it's going to steal it from the other metal, okay? That again is called the activity series, and like I said, it's on the formula chart with your polyatomic ions. The last one we're going to do is the double replacements. The double replacements, again, are not that hard in that we already know that this X is going to go where the Y is, and the Y is going to go where the X is. They're going to switch places, which is why it's called a double replacement. So let's try this out. And again, you could know that this is going to be a double because notice we have a compound plus a compound. What else can you do with compounds other than rearrange them? So I'm going to be left with silver, not nitrate, but chloride. Okay. Then we're going to have our sodium plus sodium is going to get the other nonmetal, NO3. Notice we still have metal first, non-metal, non-metal. I kept that organization, right? Metals always go first, followed by the non-metals. So let's just double check to make sure these are right. So what we have, of course, is silver is a +1, chlorine is a -1. Okay, so those cancel out. That is correct, AgCl. Yeah, I had to think about that. Sodium is a group 1 metal. Nitrate is a -1. So again, those also cancel out. So this is a very nice one. AgCl plus NaNO3. It's already balanced because everything is all ones. So that one was really easy. All right, the next one we have is lead 2 nitrate plus potassium iodide. Okay, so again, I'm going to put the lead where it was because again, the lead is not moving, right? Another way you can think about it is I'm going to put the potassium where it is because again, it's not moving, but I'm going to move the iodine there and the nitrate there. So this becomes iodide, this becomes nitrate. Okay, so knowing that lead in this particular case has a charge of 2, and I know that because of that, the charge of 2 is going to go there. Or actually, let me take a step back. All right, so the charge of 2 is for lead. Again, I know that because of this right here. And iodine is a halogen, so it's a -1. So I'm going to cross those like that. So what I'm going to get is PbI2. PbI2 is lead iodide. So I'm going to change that and let me rewrite it as PbI2. Then my potassium nitrate again is going to be K is a +1 because it's a group 1 metal. Nitrate from the periodic table from the polyatomics is a -1, so those cancel out. So it is just KNO3. So PbI2 plus KNO3. All we need to do now is balance this thing, and we're finished with this example. So because I have a 2 here, I'm going to need a 2 there, which gives me 2 potassiums, but that gives me 2 iodines. Oh, look, I already have 2 iodines. That tells me it's balanced. Okay. The next one we have FeS, which is iron 2 sulfide plus hydrochloric acid or hydrogen chloride. What we need to do is figure out what that's going to make. Of course, it's double replacement because we have compound plus compound. All we could do is switch these two things. So I'm going to put the iron where it was. I'm going to leave the hydrogen where it was. I'm going to move the sulfur back here, and I'm going to move the chlorine up there. Okay? So I already know that the iron is a 2 because, again, it was iron plus 2. Sulfur is a minus 2, so they got canceled. So I know that iron, in this particular case, has a plus 2. Chlorine is a halogen. It's a minus 1. So I'm going to cross those down there. My final thing will be FeCl2. FeCl2, let me rewrite that. FeCl2, that's my iron 2 chloride. And then again, we have, going for the next compound, hydrogen's a plus 1, sulfur is a minus 2, so I'm going to cross that down there, and we get H2S. H2S. So let me rewrite that. H2S. That's dihydrogen monosulfide. Let me erase all this so I could balance it because, again, that's a lot of stuff on my page and I don't want to get too confused. So to balance this, what I would need to do is, I see 2 chlorines here, so 2 chlorines there. That gives me 2 H's, 2 H's. Oh, look, I already have it. It's balanced. All right, guys, so that's how you do a double replacement. You just have to notice that it's a compound plus a compound. Take the second halves, switch them. Make sure that the compounds are correctly written, which again is going back to units 3 and 4. Make sure the compounds are written correctly, and if they are, it shouldn't be that difficult to balance, okay? So those are the 5 different types of reactions and how to predict the products from the limited reactant information we're given. You first identify what type of reaction it is. If it's a single, you're going to move the non-metal potentially to the other metal, depending on the activity series. If it's a synthesis, you have 2 individual things, put them together. If it's a decomposition, you have 1 compound, well, break it apart. If you have a double replacement, compound plus compound, take the second halves and switch them. Again, the activity series is only needed for the single replacement, okay? Thanks for watching, guys.